Greetings. For this lesson, we're going to look at a technique known as integration by parts. This is the last section that we'll do before we move on to a brand new chapter for the BC Calculus. It's also a big theme of what you would see in Calc 2 in college or in BC Calc, and that is different techniques for integration. So in Calc 1 or AB Calculus, we look at just antiderivatives, and then the most complicated we get would be undoing the chain rule or some rearrangements that would undo the chain rule. What's tricky about integration is there's not a specific formula other than the Riemann sums, which we don't go incredibly in depth with, but there's not a specific formula like the limit formula for derivatives. So that limit Riemann sum formula can be useful to work through. And you might someday do that if you get deeper in calculus, but there's not like a hard and fast rule to go back to sometimes. So for integration, we have to look at different techniques that we can use, and one of those is integration by parts. And you could sort of think of it as the product rule for integration, but there is no such thing. So it's a rearrangement of the product rule for derivatives. So at the top there, looking at the product rule for derivatives. And so if we have the derivative of a product, u times v, it's the first times the derivative of the second, plus the second times the derivative of the first. U dv plus v du, or left d right plus right d left. Now, rearranging. So what we did there was we took the u dv, moved it to the left, took the derivative of uv, pushed it over to the right, and we get this. Now, we're going to integrate. Now, integrating with respect to x, okay, so that means, remember the u and the v represent things that have x in them. So we're going to integrate. And if we integrate one side, we have to integrate the other side. And one of those rules is if we're integrating a difference, we can just integrate the terms separately. And so if you look and think about what would cancel out, we will get the integration by parts formula. And that is on the next slide here. So there it is. Integration by parts formula. And so here it would be used for problems like the one that you see right there, where it says the integral of x sine x. Now notice there's no limits of integration. When you don't see limits of integration, then the focus is just on what's the function. So it's not a definite integral with a numerical valued answer. It's what we would call an indefinite integral. And our focus is on what's the function, and we may or may not have enough information to figure out what the constant would be that would have been attached to that function. So thinking about integrating by substitution, now that's something we're going to do really soon in AB. Integrating by substitution just means undoing the chain rule. So if you look at that, take a glance, why would that not be an example of a chain rule derivative? Well, look at what's inside the sign. It's just an x. So if I was doing the chain rule and I took the derivative of what's inside, the derivative of x is 1, it wouldn't be this x out here. So what that's telling us is this is not something that we would get just by taking the derivative of a chain rule. Now the integration by parts formula, I haven't talked too much about that, but it's a formula. Now it says the integral of u dv, so it's saying something times the derivative of something, u dv, equals uv, the product of two parts, and then minus the integral of v du. So what we're doing is we're starting with the left side. We're going to figure out some pieces that would fit in on the right and then just continue with that formula. Now there's different ways to choose the u and the dv. Oops, there we go. And so if we were going to take this x sine x, what we could do is we could call the x the du. I'm sorry, we could call the x the u and the sine x dx the dv. We could call the sine x the u. Like, you can pick any way you want, but only one of the ways, or potentially one of the ways, will be better, or perhaps the only way to do it conveniently with the tools we have. So here are some different options of how we could set this up. We can let the u equal the x and the dv be the sine x dx. We can let the u be the sine x and then let the dv be the x dx. Or let the u just be that whole thing, the x sine x, and let the dv be a dx. Now, In order to finish the formula, look over to the right. We start with a u and a dv, but to use the formula, at some point we need a du, and at some other point we need a v. So whatever we pick here, we've got to like go and then figure out its counterpart. Okay, so look at the second and the third options here. If I were to let u be sine of x, then the derivative of that would be cosine x. If I were to let dv be x dx, then v, working backwards, because dv is like the derivative of v, then v would be 1/2 x squared. Now if you take a moment and plug those in up here, you will see that on the second part, where that integral is, you're going to get an integral that's even worse than what you started with. So not a good way to do it. Over here on the right side, if you let u equal x sine x, then your du, you'd have to do the product rule, and you would get x cosine x plus sine x dx. For the dv, if you let it be dx, that's like saying the derivative of v equals the derivative of x, so then v would be x. And that's just going to get nasty. So again, when you plug into the formula, it gets worse. So over here on the left, this is the way we want to do it. We'll go over a few methods for picking that. But I want to go back actually and do this one the right way. So let me just clear this slide and work through it as if we're doing it right. So I see I'm integrating x sine x. In general, you want to pick the u. Sorry about that. The u to be whatever is the simplest, pardon me, whatever would become simpler when you take a derivative. The dv we want to pick to be the most complicated part that we can still find an antiderivative for. So if u is x, then du would just be dx, the derivative of x. If dv is sine x, sorry, I forgot I should have attached the dx there, then v would just be, what would it be? Negative cosine x. Now look over at the formula. It's all made up of u's, v's, du's, and dv's, so we can plug in. Looking to the right there, I'm going to turn it into u times v, so that's x times negative cosine x minus the integral of v du. So v is negative cosine x, and then du is dx. Well, look what we did. We turned it into a really simple integral. So a little bit of simplifying. So on the left there, x times negative cosine x, that's just negative x cosine x. Minus a negative would be plus the integral of cosine x. I'm allowed to do that because remember, constants can be factored out. So then the negative x cosine x is there, plus, well, gee, the integral of cosine x. I said if there's no limits of integration, we're focused on just what's the antiderivative, and the antiderivative of cosine would be sine of x, and then there would be a constant there. We don't know what it is, but there'd be a plus c. And that is the antiderivative of x sine x. And you could check that by taking the derivative. So you'd have to do the product rule for the first part, you'd get some different terms, stuff would cancel out, and you would get x sine x. Here are some strategies for choosing the u and the dv. One thing there, dx always gets put with the dv. I think I said this over on the other slide there. Choose the dv part to be the most complicated part that you can still integrate. So if you turn it into something that you can't find the antiderivative of anyway, you're going to run into a mess then in the second part of the formula. And then choose the u to be a polynomial that will simplify when you take the du. Those are your best case scenarios. So what we'll do in class is we'll look at a couple examples of this, a couple more examples, and you'll see that this is one that with some practice you can get down pretty easily, and also there's a little shortcut I'll show you that works with some of the problems.